In today's video, we're going to look at section 13.1 on chi-squared. And first of all, let's just start with the example that you have pretty much the worked out view, and then we'll switch back to this page and look at a few details. So if we look at the second page, we have an example of a setting where in 1995, the Mars Candy Company claimed that the following color distribution for plain M&Ms held true. That 30% of the M&Ms would be brown, 20% would be each of the yellow or red, and that the remaining three colors would have a 10% distribution. And so basically a simple random sample of size 252 was taken, and these are the counts of the M&Ms of each of the colors. Now, if this model actually holds true, that we have 30%, 20%, 20%, and so on, then if I take 30% of the 252, we would expect that 75.6 of the 252 M&Ms should be brown. And we can see that only 38 were brown. Likewise, I went through the other categories and multiplied each of the percents times 252, and I got my expected count of how many M&Ms would be each of the different colors according to the distribution. And I can see that we don't have all of these matching up. And what chi-squared will do for us is help us decide whether this data seems to fit this proposed model that the candy company proposed back in 1995. So the second thing I did was I made a little bar graph to sketch and look at the differences between my observed count and my expected counts. And so you can see that I have my brown. Definitely the brown does not appear to fit the model. The yellow, the red, the orange, maybe those don't look too bad. Green, blue, not sure about those, but those might be in question as well. So how do we use chi-square to answer the question, does this model that the 1995 claim posted seem to still fit with this sample that we've taken? So in chi-squared, it really is a multiple proportion test. And so I'll start out and I have my null hypothesis that each of the colors that we had up above is going to fit the model that I'm proposing for the 1995. So I'm going to assume that the proportion of browns is 30%, the proportions of both yellow and red are 20%, and that the other three colors have a 10% proportion. And then in my chi-squared alternative, not all of these proportions would be equal. I don't go down and write down not equal to, not equal to, not equal to, and so on, because I'm not going to, with chi-squared, show that they're all wrong or all right. I just know that my chi-squared test will tell me that there is at least one category that doesn't fit the model. Now, remember, on all the hypothesis tests, the first things we want to do is we want to check our assumptions. And on the front side, there really are two things you're going to test. First of all, do you have a simple random sample? And then secondly, you really want to have all of the expected counts be at least 5. And now if I look at my chart, I do have all the expected counts at least 5. I have the smallest one is 25.2. If you have some categories here that are less than 5, that doesn't mean that you can't absolutely do the test. It's just if they're all at least 5, there's no doubt if you have a simple random sample and all your expected counts are at least 5 that you can definitely perform the test. And we'll look back at the other information that I had written down when we look at the next example. So the chi-squared exam is looking for these two assumptions, and now we need to find our test statistic. And our test statistic is calculated, sorry to say, but we're going to switch again, by doing this calculation. This is the test statistic. And we're going to take what you got for a category, so how many M&Ms were brown, minus how many you would expect to be brown according to the model, and take that difference squared, and then divide that by the expected. And again, it's just the numerator that's squared. It's not the denominator. So it's the difference squared divided by expected. And then we add up all of those different categories. Now, The number of categories that we have determines the number of degrees of freedom. And so, for instance, if we had had some type of a distribution of M&Ms or whatever categories we're looking at, but let's say it's M&Ms, and if you had 4 different colors, say you had red, white, light green, and dark green, and you had 4 colors, then we are said to have 3 degrees of freedom. So this little subscript down here is describing one less than the number of categories that you have, and that's called the degrees of freedom. Now, the chi-squared statistic, you can see from this formula that the difference between these might be negative, but then we're going to be squaring it and dividing by a positive number. Therefore, every single one of the little terms in the chi-squared statistic will end up being a non-negative number. So this chi-squared stat can't be negative. Our t-stat and our z-stats can be negative test statistics, but this one, it's impossible for it to be negative. So the distribution, if you continued to take samples of a particular size and developed this table, it's impossible for the test statistic to ever be negative. And so the distribution is a skewed to the right curve. It's a density curve, so the area underneath it would be 1. And we can end up finding just one side of the tail. This test statistic of 0 would mean that every single difference is 0. So you're basically never going to have your test statistic or your chi-squared value be 0. So you're looking at the upper tail when we do a chi-squared test. If the number of categories changes, say for instance, again, you have more colors of M&Ms in your distribution, then this subscript changes. And this subscript is the number of degrees of freedom, and it's how many categories you have less 1. Now, going back to this, so I'm calculating my test statistic of the chi-squared. I took how many brown M&Ms actually occurred minus the expected squared divided by the expected, and continued that with each of the different elements. Then I got my chi-squared statistic of 35.89. Now, putting this into your calculator is a nice thing to do. So if I put my calculator right up here, if I go to Stat and Edit, I want to clear out this data, so I'm just going to clear and clear that since I only have 2. And I'm going to put the 38, the 49, 54, 35, 39, 37 in. Now, I can go up here and I could put these percents in either as a decimal or as the actual percent. I'll put them in as a decimal. And I'm going to make my calculator find all those expected values. Okay. Now, I know I have 252 M&Ms that were totally added up from this category. And if I multiply list 2 times 252, I can actually get all of these little expected values here. Now, to have my calculator help me calculate the chi-squared statistic, I'm going to take how many M&Ms I had observed minus the predicted, or the expected, squared, and then divide that by the expected. Now, each of these little values in my list 4 is these little separate components of my chi-squared. Now I need to add all those up, and when I do, that will give me the 39.89. And so remember, I can quit out of my spreadsheet, go to Second in List, and I can have it sum up my list 4. Now, that chi-squared statistic, picture-wise, if I look at it, we know the distribution is going to look like this. And I know I have 5 degrees of freedom. I have 5 degrees of freedom. And so really we're looking at where does this 35.89 lie. And it actually is going to be a number way up here. And what we're trying to find is, this is the test statistic for my chi-squared value. And this is my p-value. That area above is my p-value. And so we'll use our CDF button. And if I go to second and distribution, and I see the chi-squared CDF button, and I will type in the second answer, so I'll have the 35.89 plot there, and then we need a big number, and we also need to put in the number of degrees of freedom. And remember, we had 6 colors, so we would have 5 degrees of freedom. And there's my p-value. My p-value is very, very tiny. There is very little chance that if you have this model and you collect data, it's extremely unlikely to get a test statistic like this if the M&Ms really have a model that is as these percents are showing. So we would definitely have evidence against the null. So we have evidence against the null. So we know that these proportions are not all correct. Now, unfortunately for us, we don't know who is off other than one. We do know that, looking at our spreadsheet again, that all of these numbers added up are 35.89. And look how this brown category is basically half of the chi-squared statistic is coming from this brown category. So we definitely know brown is wrong. But the question is, how do we know if yellow's wrong, or red, or orange, or green, or blue? And we actually have a way of doing that test. Let me peek over here. Well, we don't have that information here, so we'll have to add that on. And you may want to grab another little sheet of paper. But we're going to find out now whether, let's check, I'm suspicious of blue. I think blue may be off. We had 37 in our count, and we really were only supposed to have 25.2. So that one seems to be off. And again, on my bar graph, that seems to be a little bit of a differential there. So we're going to do a little test. I'm going to test whether the proportion of blue is actually equal to 10%. But I'm going to use my calculator to help me get that. We know this is really a Chapter 12 question now if I'm just looking at this. This is a one proportion z-test. And watch how I can do that one proportion z-test on my calculator. So I went to Stat and went over to Tests, and I'm doing a one proportion z-test. So I'm assuming that the proportion of blues is 0.1, but I'm getting a p-hat for blue of 37 out of 252. So I'm going to assume that this is 0.1. And I actually got 37 out of 252. And I want to find out whether we have evidence that this is different. We'll calculate what that p-hat is here in a second. Okay, so if I actually divide 37 divided by 252, we will get 0.1468. So almost 15%. On a two-tailed test, we know we're looking at this area and this area. And it ends up, if we wrote this out like Chapter 12 would have been, we would have said, well, how likely is it to get a p-hat that is greater than or equal to 37 out of 252? And then we would have doubled that because we know we're doing a two-tailed test. And we would have converted this to a z-value by taking that 37 over 252 minus what we're assuming, the 0.1, and then we would have calculated that standard error, 0.1, 0.9 over 252. And this would have given us our test statistic. And notice what I'm getting right here. If I do that math out, I'll get 2.478, basically. And if I do use my normal CDF to find this area, I'm actually going to get what is right here. Oops, 0.013. Well, I'll erase that. And there's my p-value. So if I was using a 5% significance level, I would have evidence against the null, and I would say blue is off. On the other hand, if I was using a 1% significance level, I would not say that. Okay, so it does appear that brown is off, blue is off. How about I check green? I'm going to check green real fast on my calculator. I go back to, again, stat and over to tests and, go over to tests and do the 1 proportion z-test. The blues are supposed to, the greens are supposed to be 10% as well. Now, I had 39 greens out of 252. And if I calculate that test statistic, I find out that my p-value is only 0.0037 something, which means the p-value is very tiny. So I definitely have evidence that this is not 0.1, that the proportion is not 0.1. Okay, so we can use our calculators, and what I would expect you to be able to write out is you would show your hypotheses, you would show your alternative, you would show your test statistic. You should show at least 2 components of your chi-squared calculated out, and find this, and then make your decision. And then if I ask you to go through and determine where the differences are, I'll allow you to use your calculator. You could write out something like this. You could tell me this is that you are doing 1 proportion z-tests, and you could be calculating using your calculator to find what the p-value is for each of these different proportion tests to determine whether you have significance or not. All right, so let's look at this last one, and then you'll be ready to practice. Okay, so we have a situation in here that this happens to be for 1981. You can read the information more clearly. But for 1981, these were the percents of people who were getting a PhD that year in 1981 in the different ethnic groups. And then they wanted to see if in 1994 they took a random sample and found out that 300 PhDs from these ethnicities came out with these numbers. So we're trying to find out again, does this model fit? This is called goodness of fit. You'll notice on the front page, this is called the goodness of fit test. So does the model fit? So I did a little graphic display showing if these are the actual percents. I multiplied each of them by 300 to find out these are the numbers you would expect. And notice there are actually 189. You would expect this many out of 300. And so you can see the pairwise whether there's some differentials. And some of these don't look like they're too bad. This one, I don't know about that one. That 6th category, the non-resident alien. And maybe we have a problem here with the white non-Hispanic. Okay, so we have simple random samples, and we have each of the expected counts. We don't have them all 5. So we do have 2 categories here that are actually less than 5. And so on the front, you know that they had a little bit of different information there as far as I had more than just expected counts at least 5. And remember, this is a robust test that we do want this to be true. But if we don't have this, that doesn't mean we can't perform the test. Look at how many categories you have, and if no more than 20% of your categories are between 1 and 5, then you're still good to go. Now, I have 6 categories here, which means really I should only have basically one of my categories have some count that's in this interval. And we do have a bit of a problem because we do have 2 categories. This one's fairly close to 5, but we would really like to have a little bit more data than 300 so that we could maybe bump these guys up. But we'll carry on. But I would make a note of that in your argument that you really would like more samples because you don't have all of these 5. Now notice the way I wrote down my null hypothesis this time, that the race distribution for 1994 is the same as 1981. Now I could have also said that the proportion of white, or the proportion who are in that first category, I think is going to still be 78.9%. I could have said that the proportion who are black is still going to end up being, 3.9%, and so on. So I could have written down each of those different categories, but that's, again, a lot of writing because each of those categories had different numbers. So I'm just putting down the distribution has not changed. Alternately, not all those proportions are the same. Don't just write not equal to in each of these cases. You want to write down something about the distribution being different and that at least one of them is wrong. So now we're going to calculate the chi-squared value. Chi-squared, what you got, minus what you expected squared, divided by the expected. And I would have plus, and there would be 5 more components. You can use your spreadsheet in order to help you get these values. And when I totaled up all of those 6 components of chi-squared, I got a huge value of 60.03. Now, once again, the distribution of chi-squared is always this skewed to the right distribution. And that 60 is going to be way, way up there. And so when we actually go through, if we use our chi-squared CDF button to determine what this little p-value is or what that area is under the density curve, it's going to be very, very close to 0. So we definitely know that there's a significant difference between the 1981 and the 1994 racial distributions for these PhD people. Now, if we wanted to look at, say, this one category, this non-resident alien, if I wanted to do a one proportion z-test, I could go to Stat and Tests, a one proportion z-test. I know that for the non-resident alien, we think that the percent from the previous was 0.128 or 12.8%. Now we actually had for this 6th category 80 people out of 300. And I'm doing a not equal to just to find out if there's a difference. And I calculate. And I find that the actual test statistic, if I did this as a one proportion z-test, would be a huge z-value of 7/7. The p-value, or the area above that, is going to be teeny tiny. And that's both tails, because this would be a two-tailed test with that not equal to. And so we would definitely have evidence against the null. Now I can also, let me go back here a second, if we have stat and over to tests and that one proportion z-test, you can have it draw it too. And it will draw the distribution. It will actually post down what the z-value is and what the p-value is. And that this center is, again, at that 12.8%. So it's possible to do that, and you can see that you basically don't see anything shown here because that z-value is so high up and so low down when we do the two proportion or the two-tailed test for that z-test. So you could definitely say that this category is off, and we could likewise go through and test the other categories. But we're still bothered by the fact that you really haven't sampled quite large enough to use this test, so we have to be careful about using the data and making conclusions about it. Okay, so that's it for this section, and that's plenty long enough. 23 minutes is plenty long enough.